Good morning. So, welcome to today's class. We were discussing polarization transfer. So, in this concept we have seen that if two spins are coupled, say spin A and spin X, coupled by dipolar coupling, then if we perturb one of the spin or saturate the population between two states of spin A, the effect of that will be seen on the other spin, which is called nuclear Overhauser effect. So, resonance line intensity change can be caused by this dipolar relaxation from the neighboring spin and with the perturbed energy level of one spin. So, here we have seen spin A and spin X. So, if we are perturbing spin A, the effect of that perturbation will be seen on spin X. So, for this effect to be seen, they have to be interacting through space, and since it is interacting through space, so there is a distance dependent phenomena. So, if say r is the distance between these two spins, so if distance increases, the dipolar interaction between them will increases, and therefore the effect will be becoming lesser and lesser. So, because dipolar interaction drops with a distance, and so this actually varies 1 to the power r by 6 that we have seen. So, as we move, it falls rapidly. So, NOE effect can occur only up to 5 to 6 angstrom, and after that there will be no NOE effect seen in general. We have also seen that effect of like NOE enhancement depends upon a factor that is called mixing time. So, this mixing time we had seen if we are doing a transient NOE where we apply a selective pulse on one of the spin and then we mix it for say time Tm and then we record a spectrum. So, this mixing time actually dictates how much NOE effect will be seen, and for short mixing time this is linear. So, here one can see that there is a linear, but if you have like longer mixing time, after a certain time it falls rapidly, and this falls of NOE enhancement or decrease in the NOE enhancement is due to a phenomena which is called spin diffusion. That means, in a simple term, spin loses out its magnetization to other spin and then you do not see that much enhancement. So, in short time regime like short Tm, it is a linear, and that is typically used for measuring the distance in molecules, macromolecules or biomolecules. So, non-linearity in decay of the NOE at higher mixing time is a consequence of leakage to the lattice. So, spin is leaking to the surrounding, and that contribution can vary according to cross relaxation rate, and this is called spin diffusion. Spin diffusion means spin is diffusing to the other spins or lattice, they are just losing out. So, we had seen that this NOE concept is very important in structural biology. So, you can actually do the same concept and you can take that in a 2D spectrum where you just, this is the mixing time that we discussed in the previous slide. So, you can measure here in 2D fashion, this is the pulse sequence, this we will deal in detail when we go to 2D experiment, but at the moment just understand that much, that depending upon what Tm we can mix the spins, and actually this magnetization transfer or NOE effect can be seen from the neighboring spins. So, here you can see if this spin is closer to this spin is closer to this spin, and all those they will be shown in the cross peak. Now, each cross peak is essentially reflecting the distance between two spins, and somehow if you quantify the intensity of these peaks, we can get to know the distance between these two spins. So, this NOG concept is generally used in the structural biology for measuring the interproton distances. Now, we had seen that earlier that for small molecules actually ρg is a better experiment. ρg is basically rotating frame NOG, and we had also seen that for large molecule actually negative NOE we obtained, for small molecule we can obtain positive NOE. So, for small molecules ρg is a better experiment, and rho g you do not do anything extra, but you have essentially a block which is called isotopic mixing block. So, it is like you are putting those spins in z direction and let them mix, but these are through a space connected. So, if that happens, you get actual distance constraints in a small molecule, and that cross peak sign comes negative. So, why it comes negative we will discuss later when we go to like no g and rho g in detail, but here to remember that for bigger molecules we use no g for measuring the distance between two protons. For smaller molecules like small organic molecules, we can use rho g for measuring the distances, and both of these has common phenomena, that is actually enhancement of the signal by polarization transfer, where we perturb one of the spin and look at the effect on the other spin. Now, up to this point we had done earlier. So, now let us move ahead. This also actually we had done. Population distribution happens because of no g effect. So, we see because of relaxation population redistribute, and we have seen previously that these are the population at different level. So, for a X transition, like X has a 2 transition X1 and X2, and for A you have 2 transition A1 and A2. So, difference between these population is the signal that comes for A, and these are the 2 distances that signal comes from X. So, we had seen this different population distribution and how it changes because of relaxation. So, now let us move to interesting concept of selective population inversion and how we can enhance signal of one of the spin by doing this. Now, here these 2 spins that we are considering have 2 gamma, right. They are not proton, but they can be carbon proton or nitrogen proton. So, let us consider this as AX spin system. AX means the weakly coupled spin system, like proton and carbon. Proton say on 600 megahertz resonates at 600 megahertz, and carbon will resonate at say 150, and their J is typically around 140 or 120 hertz. So, in that case they are weakly coupled spin system. So, let us consider that, and X is insensitive because it is gamma, say gamma of 13C, we know that actually it is a 4 times less than gamma of proton. So, this is 4. So, this nuclei is insensitive nuclei. So, suppose we have a weakly coupled spin system AX, where A is proton and X is X nuclei like carbon or nitrogen, which is insensitive. So, in that case here is the energy level diagram for this spin system. So, we have 4 states, state 1, state 2, 3 and 4. Now, the population of these states is, suppose we have a delta plus delta, here we have minus delta plus delta, and here we have minus delta fourth, and here we have delta minus delta. So, now 2 transition that is happening for A spin is this one and this one, A1 and A2. So, now A1 and A2, and for X it is happening X1 and X2. X is our insensitive nuclei. So, the intensity of each of the peak will depend upon the difference in the population. So, for A1 the difference is from here to here. So, that is plus 2 delta. So, this minus this, that is plus 2 delta, and for A2 this minus this. So, like here delta minus delta minus delta minus delta. So, that is actually 2 delta. That is how A1 and A2 have intensity equivalent to 2 delta, and they are sensitive nuclei. So, they have higher intensity. For X nuclei, which is insensitive nuclei, so similarly we can take for X1 and X2. So, this minus this, so the big delta cancelled out and a small delta adds up, that is 2 delta, and for again for X it is 2 delta. So, these are intensity for 2 insensitive nuclei, that is 13C suppose, and this is say proton. Now, that is typically case we have for a proton carbon spectrum, and this difference in the intensity is because of the population distribution. So, X is less sensitive nuclei, therefore, signal is less and population is also less. Now, suppose we do a trick. So, what we are doing now, the two transition that we had is essentially A1 and A2, and then for X we had X1 and X2. So, intensity for A1 and A2, that is what we looked, is 2 big delta, and for intensity for X transition is 2 small delta. So, let us do a trick. The trick is that now we selectively apply a pulse on A1, this transition. So, selectively apply a pulse 180 degrees. So, 180 degree pulse is for inverting the population. So, we are now inverting the population in this A1 transition. Okay. So, what is the effect of happening because of this inversion pulse? So, now take the difference for A1. So, this minus this is essentially A1 intensity will be state 1 minus state 2. So, that will be minus delta plus delta minus delta plus delta. So, that will be minus 2 delta, and for A2 it will be as usual plus 2 delta. So, this is for this and this is for this. Now, A1, because we applied a selective 180 degree pulse, so it inverted, and A2 remained unchanged. So, because of this inversion something happens to X transition. Now, that is very interesting. So, what is happening to X transition? So, now as we said, we applied pulse on A1. So, population level of state 1 and state 2 changed, and intensity of X1 and X2 becomes now actually 2 big delta minus 2 small delta, sorry, 2 big delta plus 2 small delta. Now, you can just go back and have this. So, 1 minus 3 is for X1. So, intensity for X1 is minus delta plus delta minus delta minus delta. So, if you see this, this is actually minus 2 delta, right. So, that is what intensity we have for X transition, that is substantial change in the X transition. Okay. So, change in the intensity of this transition from equilibrium state, that is what we calculated, is now plus 2 delta and minus 2 delta, that is a substantial change in the intensity for X spin. So, now what we did by doing this? So, earlier we had a intensity for X that was small 2 delta, now if you look at from the equilibrium it is a big 2 delta. So, that is a significant enhancement in the signal for X spin. So, by perturbing A spin we are getting enhancement in the signal for X spin, and that enhancement is substantial. So, how much enhancement we are getting? So, now because of perturbation we got it essentially 2 delta, and earlier we had 2 small delta. So, big delta, and earlier we had now, and earlier we had this, right. So, essentially we are getting enhancement of big delta divided by small delta. Here you can see if we have perturbed A spin we are getting enhancement in X spin. So, X1 and X2, and that enhancement is in tune of big delta divided by small delta. So, that is equivalent to ratio of the gyromagnetic of these two nuclei. So, gamma A divided by gamma X, and gamma A divided by gamma X is 4 times. So, for a 13CH coupled system we get enhancement factor is up to 4. So, although these two spins are of opposite sign, but enhancement is 4 times. So, if you take for nth system where gamma of H divided by gamma of n is essentially 10. So, for nth system we will get 10 times enhancement. This is huge. Perturbing A spin we are getting enhancement for X spin 4 times for a CH system and 10 times for a NH system. Okay. So, selective inversion provided us a significant advantage for sensitivity enhancement. We are perturbed one spin, we are getting 4 folds or 10 folds enhancement, but there is a problem. Problem is what? That like here as you look at, I perturb only one transition in A spin. So that means our inversion pulse has to be transition selective, so that it only perturbs A1 spin. Getting that clean pulse 180 degree is little difficult task. So and especially when it is a crowded spectrum where you do not have a transition very clearly defined, like where resolution are poor in a crowded spectrum, getting a transition selective pulse which will selectively invert one of the transition is difficult. Therefore, in those cases it can mix up and the enhancement that we are getting may not be that clean. So, to circumvent such problem, actually a method was developed and this method is called inept. What inept means? Insensitive nuclei enhancement by polarization transfer. So, let me explain each of these terms one by one. Insensitive nuclei. Insensitive means low gamma nuclei. Low gamma, what we mean? So, generally proton has a high gamma, low gamma is like where population levels are not too far apart. So, like carbon 13 and 15, phosphorus, many other nuclei are low gamma nuclei and they are essentially insensitive nuclei. So, we want to enhance the signal of these low gamma or insensitive nuclei by transferring the polarization from high gamma nuclei, which is proton. So, if you transfer the polarization from proton, which is high gamma nuclei, to carbon 13 or nitrogen 15, which is low gamma nuclei, that method is called inept, insensitive nuclei enhancement by polarization transfer, that is inept. So, what actually it is? So, it is a set of pulse that I am going to explain you in a moment, and this pulse sequence actually helps to circumvent the issue related to selective inversion, because as we see, if the transitions are not far apart, then getting 180 degree selective pulse is difficult. So, in those case, in inept case, we do not need that transition selective pulse. One can use non-selective pulse and which is called hard pulse. Like symbol for hard pulse is like a square shape and soft pulse are something like this. So, hard pulse means their bandwidth is quite high and soft pulse, that bandwidth is low, that is how they call it hard pulse and soft pulse. So, duration is short, that means like duration of this hard pulse can be of few microsecond. So, bandwidth is going to be in like 1 by microsecond, that will be in tune of say kilohertz or even megahertz. So, few microsecond this megahertz tune, and the soft pulse will be larger duration like 200 millisecond or 500 millisecond, therefore, actually their bandwidth is in kilohertz. So, even if you look at, so to selectively excite one of the transition in this pulse, you need a bandwidth of few hertz, and that means pulse has to be very long. Long pulse has its own problem. One problem that can be even non-selective, like it cannot be very precisely selective, that can leak out. So, to circumvent such problem, this method was developed where we can use hard pulse and you do not need to selectively like use transition selective pulses. So, what this pulse sequence is, let me explain you. It says that we have 2 spins. So, here is our spin number 1, which is A spin, and spin number 2 is X spin, that is why these are 2 channels. So, channels, that means a frequency channel. If you are doing experiment at say 14.7 Tesla, which roughly correspond to say 600 megahertz. So, that means proton channel will be around 600 megahertz and carbon channel will be around 150 megahertz, that is why they are 2 different channels. So, their RF synthesizer will work in different regime, and that is how they are 2 channel. So, now on A channel we are applying a first 90 degree pulse in X direction. Then we are waiting for certain time, which is tau. Then next step we are doing applying a 180 degree pulse on both channel, A channel and X channel. Next we are waiting for same time period which is tau, and next we are applying a 90° Y pulse on A channel, followed by a 90° X pulse on X channel, and then we are detecting. Now my resonance should be in XY plane, which can be detected. So that is a simple pulse sequence for inept, starting with a 190° X pulse, then waiting for a tau period. I will just explain you in a minute what actually it is. Then waiting for tau period, then applying a simultaneous pulse 180° X pulse on A spin and X spin, again waiting for a tau time period, then apply a 90° Y pulse on A spin, followed by a 90° X pulse on X spin and detecting it. So what happens because of this polarization? So this is the vector diagram. Let us understand. If I go back, first thing we did, we applied a 90° pulse on A channel. So A means proton. So suppose we were always discussing two transitions. So two vectors here, two vectors, we applied a pulse 90° pulse on A. So that means they will go to minus y. So just a thumb up rule. Now here I have drawn a circle, I have written z x y. First thing we are doing, applying a 90° pulse on A channel, 90° X pulse. So initially magnetization was in Z direction, we applied an X pulse. So you apply X pulse on Z, it will go to minus. So if it is moving anti-clockwise, it is a minus, if it moves clockwise, that is a plus. So X pulse applied on Z magnetization, it will lead to minus y direction. So that is why we have here these spins are in minus y direction, and two spins because we have a it is a X coupled system. So we have two transition, one vector shows one of the transition. So A1 and A2 both now are in minus y direction. Then I said I have to wait for some period which is tau period. Now what is this tau period? That is very important. So tau is basically will be dictated by what is the coupling constant between these two spins, and we will see in coming classes that if you keep your tau which is equivalent to 1 by 4 j, j is the coupling constant between like 13C and proton. If you keep that, now that will help you in transferring the magnetization from one spin to another spin when they are coupled through bond. So that is the tau period, tau is equal to 1 by 4 j. So if you wait for that spin and we are not doing anything. So we started like this, then we are waiting for tau period. So now in that wait period, spins will start moving in opposite direction from like minus y axis. So here is my minus y axis, and both of these spins in the second case they started moving. Second case, what I mean by, so here both the spins are in minus y direction, and then during this tau period they are like started from here and they are now moving like this, moving like this. So that is what is shown here. So now though both of these vectors are moving in opposite direction. Then we had applied 180-degree pulse on A and 180-degree pulse on X. So let us look what is happening here. So we had applied 180-degree X pulse on A. So 180-degree pulse will create inversion. So now these two guys were moving like this here, now it will create inversion, so they will move like this, and that is what actually it is shown. So here 180-degree pulse, now they change the direction and they will be going in this direction, they will be coming along plus y direction. Simultaneously we had applied 180-degree pulse on X. So that actually changes the direction of the precision. So then they will start going in opposite direction, okay, A1 and A2. Now next, after these two pulses we are waiting for, after this pulse we are waiting again for tau period. So if you look at the vector diagram, we started like this, then during tau period they were like this, and then like we inverted like this, but they were coming like this. So we applied 180-degree pulse on X. So, they changes the direction and they again are going further. Now, after again time period tau, which is again 1 by 4j, they will align along x axis. So, one will be minus x and another will be x. So, now then we are applying a y pulse, the magnetization in x direction. So, we are applying a y pulse on a spin. So, what we are doing 90-degree y pulse. So, if you apply here, if you apply a y pulse when magnetization is in x, so it will go to z direction. So, now my magnetization for a spin will be along plus z and minus z. Now, my magnetization is in z direction, for a spin it is in z direction. So, next we applied here a 90-degree x pulse. So, 90-degree x pulse, here population inversion happens. We have started both these transition in z direction, but at this stage what we have done? We inverted one of the spin, if you look at. So, then we apply a 90-degree x pulse on x spin and that transfer, the selective polarization enhancement happens on x spin. So, that is why we have now enhanced signal for x spin, but only caveat here is that both of these transition will have opposite sign, but their signal has been enhanced. That is how in inept you enhance the signal for x spin by application of this pulse sequence, which is nothing but a couple of pulses which can be given by 90 tau 180 tau 90 90. So, we achieve the enhancement in the signal of these spins. So, that is what we have done. So, finally, we get an enhancement and this enhancement is actually equivalent to selective inversion of a transition here, and consequent of that enhancement we are getting in x transition, and that will be essentially governed by gamma A divided by gamma x. So, for if we are doing this experiment or carbon proton coupled system, we get 4 times enhancement, and for nitrogen proton coupled system we get, for N15 we get 10 times enhancement. So, like selective population inversion we achieve enhancement, but of course will be of opposite direction. But inept has some disadvantage. One disadvantage we found it that both the signal for x spin are coming in opposite direction, and there can be intensity anomaly. So, incorrect relative intensity can occur because of different spin multiplication. So, for simplicity we considered only 2 transitions, one was like this and another was like this, and we found that if we invert one of these x transition, one was like this and another was like this. But what happens if there is a spin multiplet? So, then we have a problem, because then again we cannot get a clean enhancement. The another thing that we looked at, one of the parameter that was there 1 by 4j. So, now this j is playing important role, because that dictates how much tau we are keeping. So, if the strength of heteronuclear j coupling is different, then transfer of magnetization or population inversion can be different. So, this dictates how much transfer it is happening. So, 2 things, j coupling and spin multiplicity actually dictates the transfer efficiency in case of inept. So, to get rid of that, what we need to do, we will look at this in next class. Based on today's lecture, if you have any question, do not hesitate to ask us, we will try to resolve it. Thank you very much.